Greetings everyone, I'm Purna Chandrasekhar. I'm going to talk about analog to digital converters as a part of my ELP 101 project. So electrical and electronics are basically divided into two domains. One is the analog electronics and the other is the digital electronics. Let's try to understand the basic differences between these two things. So analog versus digital signals. We have an analog signal, which is generally a time varying signal bound between certain values. And then the voltage can assume infinite values in this particular range. And thus the signal is a continuous signal. Whereas a digital signal is a signal that represents data as a discrete valued sequences. And this type of signal can only take one value from a finite set of possible values. In this graph, you can see it can take either 5 volts or a 0 volt. So thus, since digital signals are more prominent in today's age, it is very important that we convert analog signals to digital signals and vice versa. That is where analog to digital converter comes in handy. So an analog to digital converter is a device that converts analog signals to digital signals. So analog signals being passed into the converter, and the output is a digital signals converted and represented by bits 0 and 1. There are various types of ADCs, but we are going to discuss about a direct conversion ADC. So a direct conversion ADC is an analog to digital converter, which uses a linear voltage ladder along with a comparator at each phase of the ladder. And this comparator is responsible for comparing the input voltage to the given reference voltages. Now, this voltage ladder is typically constructed from a series combination of many resistors, and often it is also constructed from capacitors in many cases. So you can see this is a 2-bit direct conversion ADC, where we have this voltage ladder, which varies from 4 to 0 volts, constructed by 4 equal resistance connected in series. We have an analog input signal. We have 3 comparators, which are based on op amps, which give 3 inputs, and the D0 is initialized to 0. And all of these 4 inputs are fed into a 2-bit priority encoder, and then it gives a digital signal as the output. And we're going to analyze the functionality of each of these components in detail. So if you understand the components of direct conversion ADC, the first component is an op-amp based comparator, which is responsible for comparing the input voltage to a particular reference voltage. We have a priority encoder, which takes in bits of data and then outputs a digital signal. So let's analyze the op-amp based comparator first. So an op-amp in a closed circuit configuration can be used as a voltage amplifier, as we have seen in our in one of the experiments of our ELP course. This is achieved by connecting the output terminal to the inverting terminal of the op-amp by a feedback loop. So you can see the output terminal is connected to the inverting terminal using a feedback loop in both of these cases. However, an op-amp can also be used as a comparator through an open circuited configuration without this feedback loop. So here's the schematic diagram of an op-amp based comparator. In this configuration, the input voltage is given to the non-inverting terminal. The reference voltage is given to the inverting terminal. Now the expression for output voltage is given as V out is equal to A times the non-inverting voltage minus the inverting voltage. And here A is a constant, which is considerably large. Now in this case, the non-inverting voltage is the input voltage, which is V input, and the inverting voltage is the reference voltage. So in this case, the output voltage would be A times V input minus V reference. So analyzing different conditions here, when the input voltage is greater than the reference voltage, V out is positive, and since A is considerably large, after some time, the output voltage would reach the saturation voltage of the op-amp, and thus would give the value high, or represented by Boolean value 1. In case 2, when the input voltage is less than the reference voltage, the output voltage is negative, and since A is considerably large, V out reaches to negative of the saturation voltage of the op-amp and gives the value low, or represented by Boolean 0. And this is a graph of the output given by the op-amp based comparator. So when the input voltage is greater than the reference voltage, V out is the saturation voltage of the op-amp after it is increasing linearly. And after some time, it increases linearly. When the V input is less than V reference, then it reaches to a saturation point in the negative side. And then the V output is given by negative of the saturation voltage of the op-amp. Now, there are two types of op-amp based comparators. One is an inverting comparator, where the input voltage is given to the inverting terminal, and then the reference is given to the non-inverting terminal. Whereas in a non-inverting comparator, the input voltage is given to the non-inverting terminal, and the reference voltage is given to the inverting terminal. So comparing this in terms of conversion, if we see, the peak of the analog signal here gives the lowest value, whereas the lower peak of the analog signal gives the highest value in case of an inverting comparator. Whereas in case of a non-inverting comparator, the highest peak of the analog signal corresponds to the highest value of the digital value, and similarly in the other cases as well. Now let's analyze a priority encoder. So a priority encoder is a circuit that comprises of multiple binary inputs, and this reduces to a smaller number of outputs. This priority encoder is built through logic gates, and this is a 4 to 2-bit priority encoder shown in the figure. The priority encoder typically contains 2 power n input lines, and which are reduced to n output lines after the values are computed. The encoder also represents the highest priority input among all the input lines, which are going to see the input priority sequence is what we're going to study in the forthcoming slides. It's a truth table of a 4 to 2-bit priority encoder given here, where X represents the don't care scenario, where we do not care about what the value, that particular variable is assuming. So now that we have studied the individual components, let's start to assemble the components. First, let's analyze the comparator circuit. So for convenience, the reference voltages are varied from 0 to 4 volts. And in an actual case, these conditions can be varied as per the requirement. And then we are varying the voltage from 4 to 0 volts. There's a ladder of resistances R, of resistance R, which are in four in number and connected in series. And then there is an input signal which is given to all of these comparators. So here D0 is 0 as the D0 wire is grounded. Now for output D1, the reference voltage here is 1 volt, and thus we input greater than V reference means that the D1 is positive or high, and V in less than V reference means that D1 is negative or low. And similar case happens with D2 and D3. Only thing is that for D2, V reference is 2 volts, and for D3, V reference is 3 volts. Now analyzing the priority encoder. After the comparator circuits gives the outputs mentioned in the previous slide, these inputs are passed to a priority encoder. Now, the priority encoder allocates a priority level to each individual output, each individual input, and thus in this case, the priority level would be D3 greater than D2 greater than D1 greater than D0. So for V in less than 1, all the comparators here gives the output low. Thus Q1, Q0 would be equal to 0, 0, or the Boolean representation of 0. Whereas if V in less than 2, then only the comparator D1 gives the output high. Thus Q1, Q0 is equal to 0, 1, or the Boolean value of integer 1. If V in less than 3, then comparators D1 and D2 gives the output high, and thus Q1, Q0 is equal to 1, 0, or 2. And here, since the priority encoder is giving priority to D2, we get the output as 1, 0. And then for V in less than 4, comparators D1, D2, D3 gives the output high. Since priority encoder allocates D3 as the priority value, we get Q1, Q0 as 1, 1, or the Boolean representation of integer value 3. This is a truth table for the priority encoder in this particular case, where we're varying the input voltages, and the comparator gives these outputs, and then these outputs are being analyzed by the 2-bit priority encoder, and a digital signal is being computed by this setup. So thus, by this process, an analog signal gets converted to a digital signal. In this way, an analog signal passing through this circuit gets converted to a digital signal. Now, the significance of ADCs are that ADCs are used in digital oscilloscope that we see in labs to convert analog signals to digital signals for display. Multimeters also use ADCs to convert the analog signals to digital signals and show the reading. Mobile phones also have ADCs to convert the analog voice signals to digital signals for transmission. In conclusion, we have seen op-amp-based comparators used in ADCs. Op-amp are also used in many other devices, one of the prominent one in this context being a digital to analog converter. Lastly, I want to thank my professors and course coordinators of ELP 101 course for giving me this opportunity, and thank you.